want to stay and just do some stargazing with us, we'll just kind of meet at the front of the pavilion here, and then we'll just go the short distance to, we have 6 telescopes set up. Some of our volunteers have kindly offered their time and telescopes to show you a bit around the night sky, so we'll go from 9:30 to 11. And then we'll see you again back here tomorrow. So, we'll get on with our guest speaker here.
Can I just ask,
Oh, okay, sure.
Hi, I'm the donation lady. So if you are staying overnight, we ask for a donation of $20 to just pay for the incidentals and things that we have to do to get ready for this. And if you are not staying overnight, but you would like to donate to the public programs and things that are going on, then I'm the person to see. My name's Lori, and I've got the bucket. So if you want to see me, I will any donation gratefully accepted. Thank you, David. All right.
Thanks, Lori. Okay, we're actually really lucky. I mean, for those of you that don't know it, I mean, this is really the kind of center of astronomy for Canada in a whole bunch of ways. Not only do we have UVic, but we've got the Dominion Astrophysical Observatory and the Hertzberg Institute of Astrophysics up there. And between the staff and the students in Victoria here, we just have like no end of really great guest speakers. So tonight we're very lucky to have Dr. Rita Mann. So Dr. Mann is a researcher at NRC Hertzberg Astronomy and Astrophysics. She earned her honors BSc in physics at the University of Victoria and her master's and PhD in astronomy at the University of Hawaii. She then returned to Victoria with the Plaskett Fellowship at NRC Hertzberg. She uses a powerful new telescope called ALMA, which is down in Chile, which is very sensitive to the conditions in which our planets are born, to answer questions about origins of our solar system as well as other extrasolar planetary systems. So please give a nice warm welcome to Dr. Rita Mann. And there'll be time for questions and answers after her presentation. Do you need a laser pointer, or do you have one?
I gave it.
Is that one? Just take a minute for this projector to warm up and we'll be on our way. There you go. Thank you very much.
Yes, can you hear me at this volume?
Can you hear her?
No.
No.
Yeah, it doesn't, is it picking up my voice at all?
Yes, it is.
That's better, I'll just have to speak right into it. Lori, do you know why the side of the cut off? It's actually...
Yeah, slide the projector over.
This should be fine, actually. There's just a little bit of a repeat strip here, but I don't think it's blocking out too much. Thank you so much for having me speak here tonight. Thank you, Lori, for asking me to speak. I think I was here about 5 years ago when I first moved back to Victoria, and I'm glad to see this is such a great turnout for an annual event. I think you guys are going to have a wonderful weekend. The weather's been amazing, so get ready for some stargazing tonight, I guess. So I wanted to talk a little bit about some of the work that I find very exciting right now, and focus really on the Canadian contributions, what Canadian astronomers have done to answer questions. So So the first project that I will speak about is a really interesting one. It's one where we are using sub-millimeter wavelengths. They're a different kind of way of looking at the universe in a way that has never been, the universe has never really been looked at in this way before. And so we're discerning some really exciting information about how planets form using sub-millimeter telescopes, particularly this revolutionary new telescope called ALMA. And we've used it to look at this particular region in the Orion star forming region, which many of you are probably familiar with, to take these very images, these very detailed and beautiful images of planets forming around young stars, very much like our sun and Orion. So let's take a step back and start with the constellation of Orion, which again, most of you are probably familiar with. If not, it's up during most of the winter night sky, and you're probably looking at Orion if you see 3 bright stars in a row. That's Orion's belt. These are Orion's shoulders, Orion's knees. This is the sword of Orion and the head. And it is, I think it's up in the early morning hours, so if you're up very early tomorrow morning, you might catch a glimpse of Orion. The stars that make up Orion are very, very massive monster stars. So here are some of the most well-known stars: Betelgeuse, Bellatrix, Saiph, and Rigel. These are stars that are at least 10 to maybe 30 times more massive than our sun. So it would take up to 30 of our own suns put together to produce one of these very bright stars. So they're very bright, they're very luminous. And the region that we've really focused on to understand how planets form is this region below the belt of Orion and the sword of Orion. The second star of the sword of Orion, it's actually not a star. If we zoom in on it using Hubble Space Telescope imaging, we actually see it's a glowing cloud of material. This beautiful image taken by the Hubble Space Telescope reveals a lot of detail in this region. And we find that it's actually a stellar nursery. This is where young baby suns have just been born. There's tens of thousands of young stars, which look very much like what we expected our sun to look like when it was first born. And they're surrounded by perhaps baby solar systems. So this region, if we zoom in further into the heart of the Orion Nebula, just in this region, we zoom in, we find some more very, very massive luminous stars. The most massive is about 40 times the mass of our sun. So 40 of our suns combined would produce this one massive star. And this star is very important for several reasons. One is most young stars, so these young red stars, are sun-like stars. Most stars actually form very close to one of these massive stars. So the majority of young stars form in regions like this in Orion. We also know from detailed studies of our solar system that our young sun formed near a very massive star that ended its life as an explosive supernova. And these supernovae are very important because most of the materials that are vital to the existence of life were formed within these massive monster stars. And that material becomes liberated into the surrounding medium and gets incorporated into the next generation of young stars and forming solar systems through these supernova explosions. And so they're incredibly important for various reasons. And so studying how these young stars form very close to this massive star is important, not only for the vast majority of stars, but also for our own sun, which formed in a very similar environment. So these young stars, they're about 1 million years old, which doesn't seem very young, but considering our sun is about 4.5 billion years old, and it's only about halfway through its life cycle, this was really the start of a young sun being born, the first 1 million years. So let's look at these young stars in even more detail with the Hubble Space Telescope. So these are Hubble's images of the young stars, and they show that they're actually surrounded by these dark lanes, these kind of flattened plains of dust and gas surrounding them. And these, we call these protoplanetary disks because we expect them to be where planets form. We think they're the birth sites of planets. We think they're the precursors of our solar system. And the reason we think this is that if we look at our solar system and we line up all the planets in a row, we see that they actually lie in a relatively narrow plane. They Planets all orbit the sun in the same direction, and the planets have nearly circular orbits. And so it's a fairly natural explanation that they started out in this flattened disk of material and formed out of that. And if we fast forward the process a bit, we see that material within the disk actually clumps together and forms larger and larger bodies until the gravity of these bodies becomes large enough that it starts to pull in all the material in its orbit around its young sun, until it's basically cleared away, gravitationally pulled onto itself all of the material within its orbit around its young stars. And that's basically an artist's depiction of what the birth of a planet looks like. It's cleared out this region in the disk. And so, since Hubble is showing that the majority of these young sun-like stars are surrounded by these flattened planes, these protoplanetary disks of material, we believe them to be young solar systems in the making. And that's why we've focused so much attention on them. So let's look in even more detail with the Hubble Space Telescope images. So here again are those very massive stars. This is the 40 solar mass, the star that's 40 times the mass of our sun. It's a very massive star. And these are again the young suns that have just been born. And we see that they're actually, if we blow them up even more, they're surrounded by these cometary-like features. They're literally material from that disk is being boiled away. It's being evaporated because of the very high energy UV radiation coming from this massive star. Because it is so much more massive than our sun, it's putting out a lot more higher energy radiation, and that radiation is literally destroying these disks. And now we have hundreds of such images showing the destruction of these planet-forming sites around young suns in Orion. And this is just some of the collection of detailed images showing this taking place. And in each case, the bright heads of these protoplanetary disks, the bright heads are facing that massive star and the tails are facing away. So Hubble has been very important in showing this hostile environment near massive stars, this environment that's very hostile potentially to planets forming. But the Hubble observations kind of stopped there. They showed that the region was destroying the massive, the protoplanetary disks, but it couldn't show how quickly that material was being lost, and crucially, if there was perhaps enough material left remaining to potentially form solar systems like our own. And so the question remained open for many years: can planets like our own form in Orion despite this hostile environment where the high energy radiation is destroying the disks? So how do we answer this question about these protoplanetary disks? Well, the Hubble Space Telescope images, because it works in the optical, it's sensitive to the same wavelengths that our eyes are sensitive to, and so we're very strongly seeing the young stars, just like we look up at the sky and we can see all the young stars. But if we move to a slightly different wavelength, to say a submillimeter wavelength, these young stars actually disappear. So if our eyes worked in the submillimeter, we would instead look up at the sky, the stars would disappear, and those flattened planes of disk material, those protoplanetary disks, they would start glowing brightly. And that's why the submillimeter wavelengths are so important in order to understand how planets form. So in this image, we have submillimeter observations of the exact same stars that were imaged here with Hubble, except that now we are detecting those glowing protoplanetary disks. And now we can start to say something for the first time about, is there enough material there to form massive planets? Is there enough material there to form Earth-like planets? And that's why the submillimeter wavelength has been so exciting. And it's a relatively new field of astronomy. It's one of the last windows that we have into our universe. And the reason being that it's very challenging to observe at these wavelengths. An analogy one of my colleagues used many years ago to describe observing at submillimeter wavelengths is that it's like observing with an optical telescope, but in the middle of the day at noon with your telescope on fire. So your telescope is emitting very strongly at submillimeter wavelengths. The sky is emitting very strongly at submillimeter wavelengths. It's very challenging to detect these faint signals from these planet-forming disks around young stars in regions like Orion and even further away. Project called ALMA, which stands for the Atacama Large Millimeter and Submillimeter Array. This is a project that's been 30 years in the making and has just recently, it's going to be completed, I think, at the end of next year. So it'll finally be in full science operations mode. It's currently still being constructed, and it's an array, actually. It's not a single telescope, but it's an array of 66 separate submillimeter telescopes that work together to produce the single most powerful telescope ever built at these wavelengths. And these telescopes they move. They're not stationary. They can move and spread out over baselines up to 16 kilometers in size, and that mimics a single telescope of that size. And so the amount of detail that this telescope can capture is just unbelievable. The observing site for ALMA is located in Chile at an altitude of 5,000 meters in this desert called Chajnantor, where it's exceptionally dry. It's above most of that atmosphere that's emitting so strongly at these wavelengths, and that's crucial in order to be able to make these observations. You have to be at a high site. It's even higher than Mauna Kea in Hawaii. Again, the wavelengths that are being explored, these submillimeter wavelengths, this is a new way of looking at the universe, and so the opportunities for discovery are vast. We've never really seen the universe at these wavelengths, and particularly for the field of planet formation, the discoveries are expected to be very fruitful because we've really had no way of studying these protoplanetary disks except for indirectly through these optical observations in the past. Canada is one of 19 partner countries that's involved in this telescope, and it plays a strong leadership role. Even some of the receivers built for this telescope were actually built right here in Victoria at the Hertzberg Institute. And the expertise and technology assembled at ALMA make it the most ambitious astronomical project on Earth. And because of Canada's leadership role in this observatory, we've had access to some of the earliest images ever taken with this telescope during its early science phases. And these are them. So across the top, we've got the Hubble Optical Space Telescope images of these young stars in Orion, where they're surrounded by these protoplanetary disks, and the corresponding ALMA early science observations, which show these protoplanetary disks glowing quite brightly. And since we're able to detect them directly, the disks, we were able to measure their masses, find out how much material was remaining in them. We were able to finally say that these massive stars, this 40 solar mass star, is destroying protoplanetary disks, which are located within about 1/10 of a light year away from it. And this led ALMA to put out a press release on this, based on this work, called Death Stars in Orion Blast Planets Before They Even Form, showing this bright, massive Death Star, I guess, destroying the young protoplanetary disk around a young sun nearby, but leaving the massive disk around another young star that was located further away, leaving that disk intact, because it was just 1/10 of a light year. That was the distance at which the massive star was destroying the planet-forming disks. And if we look again at that large image of the Orion Nebula cluster, we see that a distance of 1/10 of a light year is actually quite small. It doesn't encompass that large a fraction of the young stars that are born in this region. And so there's still thousands and thousands of young sun-like stars, which can still potentially form protoplanetary systems like our own. And that's very exciting. This is the first time that we're able to show quantitatively that the effect of this massive star is limited to a fairly small region. And our prospects for planet formation are quite high. Another one of the interesting observations or results to come out of these submillimeter observations in recent times with Orion was this study of multiple star systems. So most stars are not like our sun. They're not alone. Most stars are part of multiple systems. So they're either double or triple or even higher order multiple systems. And so this is just a little comic to show how it might not be that normal to have just one sunrise and one sunset in this case. They're looking at 4. stars. And so we looked at a young star, a double star system in Orion. This is the double star system taken with an image of it taken with the Hubble Space Telescope. Shows a fairly substantial disk around the first star, and no evidence of a disk around the second star. And this was not surprising because all previous observations had shown that these double star systems, just by virtue of their orbit, would destroy the protoplanetary disks around, most of the time, both stars. And so this was interesting because there was one star that was still intact. And so we looked at it in the submillimeter to see how much mass is there. Is this potentially a planet-forming disk? And we were very surprised. These are the submillimeter observations of this double star system. We were surprised that there's two disks. There's one around each of the stars. And even more exciting is that both of them are massive. Both of them are massive enough to form our solar system. So you could have two solar systems that are located quite close to one another. And that's very exciting for several reasons, not just because it increases the likelihood, increases the prospects for planet formation, because now we can include individual stars in these multiple systems, which make up the vast majority of stars in the sky. But also from a sci-fi perspective, when you think about if solar systems were to form, if we fast forward and solar systems are forming around both of these stars, and life were to evolve on one of the planets around one of these stars, they would be in traveling distance to the neighboring solar system, and that's just very cool. Submillimeter observations, they're very complicated, so you actually get a lot of information from these single observations. You can also study the motion of the gas in the disks, and you can actually see it rotating around the young star. And one of the other cool things about this is that you can use this to actually study the stars themselves. You can use that orbital motion and constrain how massive those stars are. It's very difficult to measure the mass of a star, and this provides an independent way of doing that. So by studying the disks, we can also learn more about the young stars. And this is just part of the reason why ALMA and submillimeter observations are so revolutionary to many fields in astronomy, not just the planet formation. And this is some of the latest work to come out of ALMA. These are some of the most detailed observations ever taken of these protoplanetary disks, and they're extremely exciting. I can't understand how exciting these are. So basically we have these flattened disks which show these very dark concentric lanes that have been carved out, and really the only plausible explanation we have for these concentric rings is that these are protoplanets that are forming within these disks, and they've cleared out within their orbit. They're clearing out the material because their gravity has grown large enough that they're able to collect all the material during their orbit around these young stars. And so we have multiple planets forming simultaneously in both of these disks. This is two slightly different wavelengths. It's the same disk, and this is TW Hydra, which is a very nearby disk. And this is even more exciting because this very central dark annulus that's being carved out here is at a distance of 1 astronomical unit from the central star, which is the same distance that Earth is from our sun. So we're looking at the formation of a planet at an Earth-like orbit. So it could potentially be an Earth-like planet right there, and that's truly exciting because it's a direct confirmation of the idea that we have of planet formation works like this, that several planets are forming within these disks at different radii at the same time. So for the first half of the presentation, this is kind of like a bit of a summary. So we found that massive stars are not that destructive to planet formation, which is very exciting because the majority of stars form near massive stars, and even our sun formed near a massive star. So it's not that difficult, it's not that unique to form a solar system like our own. The overall prospects for forming planets are quite high, since this destruction radius is only about 1/10 of a light year. It's a small distance in astronomical terms. These double star systems can also give rise to potentially double solar systems, which is very cool. And with telescopes like ALMA, it's just a very exciting time where our understanding of planet formation is already become revolutionized thanks to the early science observations that have come out of this telescope. And it hasn't even begun its full science operation. So stay tuned for lots of news from the ALMA Observatory and lots of groundbreaking observations that really help uncover how just to further place this work in context, I've been talking a lot about the initial stages of understanding our origins, which is by studying these protoplanetary disks, which eventually form planets like our own and solar systems. You can also study our origins by understanding the final stages, which is not only detailed knowledge of our solar system, but also looking outwards at other extrasolar planetary systems, of which there are almost 5,000 candidates to date. I think 3,500 have been confirmed to date, and this is also very exciting work that helps us place our Earth and our place in the universe in context. And Canadians have had a very vital role in this part of the work as well. So let's start by taking a closer look again at our solar system. So again, if we line all the planets up, we see that there's kind of an order to our solar system. In terms of the planets, we have the 4 dense, rocky, small planets, all located very close to the sun. So Mercury, Venus, Earth, and Mars are all located very close to the sun, while the low density but very large and gas-rich planets, Jupiter, Saturn, Uranus, and Neptune, are located further away. And this makes sense in the context of our planet formation models within these protoplanetary disks, because we expect that material in the disk located really close to the sun is very hot. And so most of the gas, most of the ices, most of the material is actually evaporated at these very high temperatures very close to the sun. And so you're left with a very small amount of rocky materials, minerals, and iron-rich materials. And that's exactly the kind of material that these planets are all formed out of. As you move further away from the sun in the disk, the temperatures cool down and gas starts to not be evaporated so much. And so there's more gas as you go outward. And there's also more rocky material as well, just because there's a higher density and larger surface area in that disk further out. And so you can form much more massive planets further out. And you can also start to pull in a lot of that gas that survived at these cooler temperatures that exist further out. And so this makes this is a fairly simple way of looking at our solar system. So how do other extrasolar planetary systems kind of fit into this picture? Well, first, I guess I'm going to go over the main methods for detecting extrasolar planetary systems. So I'll do like a quick primer on the 3 main methods. The first one is this radial velocity variation method, which was pioneered. It was actually invented by Canadian astronomers. I'm sure many of you know Gordon Walker. He lives here in Victoria. And Bruce Campbell. They actually invented this technique of looking for these variations produced in a star. And basically, they're looking for wobbles that are produced on a star due to the presence of a planet. So a planet and a star will actually produce these pulls on each other, these gravitational wobbles, and they show up as these radial velocity variations, which you can measure using their method. And even though they detected the first extrasolar planetary system, they were not quick to claim a firm detection, because the atmosphere at the time in exoplanet science was very skeptical. And it's hard to imagine now that we've confirmed 3,500 extrasolar planets. But back then, there was a lot of skepticism, and so they published their data, but they were not, even though they thought they had seen an exoplanet, they were not going to claim that detection. That feed actually went to a different team, unfortunately, using the method developed by Gordon Walker and Bruce Campbell. The team Mayor and Kilos in 1995 published this discovery of a planet, a very massive Jupiter-mass planet around the star 51 Peg. And this is basically the first, claimed as the first detection of an extrasolar planet. And it really kick-started this entire field. After that, the number of detections went up exponentially every year. And this discovery was very weird. It was of this very massive Jupiter-mass planet, which is located very close to its host star, which is a sun-like star. It's located at about 1/10 of the distance from the sun to Mercury. So it's very close in, and it's a very massive planet, it doesn't make sense in terms of our solar system because we don't have one of these. And this is the radial velocity, those variations that I spoke about earlier. Using this method, hundreds of planets were found, and a lot of them were these hot Jupiters, these massive planets that don't exist in our solar system. We have no analog for this. So it's very puzzling that found so many of them orbiting very close to their host star. Other planets, other exotic new worlds that showed up were these super-Earths that we also don't have in our solar system. They're these planets that are much more massive than our Earth, but not quite as massive as Neptune or Uranus, which are the next most massive planets. So again, we don't have these, but they seem to be making up a majority of the detections that were of extrasolar planetary systems. Another way to detect extrasolar planets is a more direct method, and this is also one that's been pioneered by Canadians. It's called direct imaging, and basically use very sophisticated optics called the coronagraph to block out the light from the central star and then directly image the protoplanet. There's a lot of analysis that goes into this, sophisticated analysis tools that are needed in order to subtract out the contribution from these incredibly bright stars. The planets are so much more faint than the star that it's very difficult to do this. In our very own in Victoria, we have Christian Marois, who actually was responsible for, him and his team of Canadians were responsible for the detection, the direct detection of exoplanets, the first direct detection. And it was around the system HR 8799. And initially they detected these 3 planets, and then 2 years later, so they published that in 2008. 2 years later they found a 4th planet in 2010. They were able to publish all 4 of these candidates rotating around the host star, and so that's very exciting, and it's a much more interesting way of looking at the planets because you can study them more directly. You can get more information about them directly. With the other 2 methods of detecting extrasolar planets, you're looking at the planet properties relative to the star. And there's already been a new generation of instruments built, and in particular, Canadians have been a part of this Gemini planet imager called GPI, and it's been undergoing a survey which will end this year. It's been 2 years since 2014, where they're looking at 600 of the very nearby young stars to directly detect the young planets around them. And so these are 2 systems in which planets have already been detected using this GPI, this new instrument that Canadians have a strong connection to, that Canadians have been responsible for helping build. And that's 51 Eridani, and these are both Jupiter mass planets, and this is Beta Victorious, another nearby star, and these are... The third method has been probably the most successful to date, and it's transit observations, and it's been wildly successful thanks to the Kepler Space Telescope, which is basically trained to look at almost 150,000 stars in the sky to basically see the transit of a planet as it moves across the in front of its host star. And these are images to show the transit of Mercury that occurred just a few months ago, which was very exciting to see. But it illustrates exactly the same method that Kepler uses, basically just to look for a dip in the brightness of the host star as the planet moves in front of that star. And so there's a dip in brightness that occurs, and Kepler is able to very sensitively pick out these dips in brightness. And so this is an image of the Kepler Space Telescope, and it's looking at about 150,000 young stars located within this field of view. It's near the constellation of Cygnus. And it was focused mostly on stars like our sun. That was its prime focus. And so one of the most interesting results from this survey done with Kepler is this shows the number of planets as a function of their mass. So we've got, on this side, we've got the very low mass planets like Mercury and Venus, go up to Neptune, Uranus, and the very high mass Jupiter and Saturn. And the big takeaway point is what's going on right here in the middle. In between an Earth mass and a Neptune mass is where the majority of the discovered extrasolar planetary systems are. And these are what we call now super Earths. There's no analog to them in our solar system. We have nothing in between Earth and Neptune in our solar system, but they make up about 80% of the expected planets in our entire Milky Way galaxy. Based on the Kepler study, we expect 80% of all planets in our galaxy to be these super Earths, and that's very strange because it's not like our solar system. Some other key results is that most of these planets are found around stars that are lower in mass than our sun. So our sun is actually not the most common host for planetary systems. It's actually stars that are much smaller, much less massive than our sun, which actually make up the vast majority of stars. There's actually like 7 to 8 much lower mass stars per every sun-like star in our solar neighborhood. Another interesting, another focus of these studies has been to understand when these planets are within the habitable zone, which is what we think of Earth. It's in this habitable zone, which is when a planet is located within a range of temperatures for which water is able to cool as a liquid on the surface of these planets. And so for our solar system, Venus is right on kind of the inner edge of our habitable zone, and Earth is smack dab right in the center of it. And so one of the ways in which we can start to search for life on these other planets is by first deciding whether they're in this habitable zone, if they have the right temperature. It's also called the Goldilocks zone. So it's not too hot or not too cold for water to exist. And the first planet that was validated to lie in the habitable zone is this planet, Kepler 186f. And it orbits a star that's much less massive than our sun, but is much more common in our Milky Way galaxy. And it lies right in the habitable zone. And now, I think of the 3,500 planets, 21 of them have been validated to lie within this habitable zone. And the most exciting recent result, which many of you might have heard of, on Wednesday, just a couple of days ago, there was a press release that came out from ESO, which claimed a detection of a planet that was slightly larger than Earth, about 30% bigger than Earth, orbiting the nearest star system to us. It orbits the star Proxima Centauri. So this is kind of an artist's impression of what the sky might look like on this planet, which is just slightly larger than Earth, around the neighboring star to us, Proxima Centauri, which is about 4 light years away. And Proxima Centauri is part of this triple system where Alpha Centauri, A and B are the first two, the more massive stars, more close in mass to our sun. And they orbit each other quite closely. They're about 40 AU from each other, about the distance from the sun to Pluto. Whereas Proxima Centauri, I think, is tens of thousands of AU away, so quite a bit further. And so this is very exciting for many reasons, one of which is this suspected slightly larger than Earth-sized planet is actually in the habitable zone of Proxima Centauri. It's located quite close to it, but because Proxima Centauri is, I think, about 14% of the mass of our sun, it's quite a bit smaller, it's quite a bit less massive, and so its temperatures will be quite a bit lower, and so the habitable zone is actually quite closer in. And so it'll be really interesting to see it's exciting already that there's an Earth-like planet so close to us, but further studies will obviously be needed of these potentially habitable planets. Ideally, you'd want to study their atmospheres and find out if they're truly habitable like the Earth, or if they're, they could be like Venus, which is a planet which looks like it's in the habitable zone, but is very hostile to the emergence of life. So anyways, this was a very, very exciting result to come out the last few days, and this was discovered using radial velocity radial velocity method. And I think their project is called this pale red dot, so I encourage you, if you want to find out more information about that planet, you can go to their website. I think they even have some social media accounts under this name, and so you can learn more about this system. And this is cut off, but shows our sun, and Proxima Centauri is only about 4 light years away, and this is Alpha Centauri A and B. So this is my final slide. So some of the key conclusions from the exoplanet discoveries has been, over 3,500 exoplanets have been confirmed to date. Many of them, almost 600 in multiple planetary systems. 80% of these are super-Earths, so planets that have no analog in our solar system, which is very interesting. Small stars, which are much less massive than our sun, are actually most likely to host planetary systems, so maybe our solar system is not that common. And based on these studies, there's estimates that there's actually more planets in our galaxy than there are stars. So if the Kepler results hold, which again, they just looked at a small patch of the sky, but from that, they can sort of infer that if that patch is very similar to all the other regions in the sky, then there should be more planets than stars in our galaxy, and that's very exciting too. And at least 21 of these confirmed exoplanetary systems are potentially habitable, but will require a lot more further detailed studies with really even larger telescopes than we currently have in existence, as well as space-based observatories like the James Webb Space Telescope, in order to really tell us if they are habitable planets. So I'll close with that, and I'll be happy to answer any questions. Thank you. So there is a bias. There's definitely she was sort of wondering if there's a bias in how we're detecting planets, and if that's stopping us from perhaps detecting the smaller mass planets closer into the smaller mass stars. And there's a lot of biases already in the two main methods for detecting planets, the transit and the Doppler, which is that Doppler is the radial velocity variation, it's sensitive to very high mass planets. So these Jupiters are the ones that they're most sensitive to, so you can't detect the lower mass ones without the next generation of instrumentation. We're not going to be able to detect those, so you're right about that.